Almost done? Anybody need more time? We're all done? Done? Okay. Let's get it started. Let's see what you learned last class and what we're going to see today. Any question? We can solve them later. You have a question about the? Sorry?
Picks up.
You should use one of those rules, complement rules. 1 minus, because we had, I don't remember exactly what was that, but when we have, for example, probability of A, you could find probability of not A. We're going to solve that, okay? We're going to solve them, don't worry, okay? Let's see what we had, okay?
I got it wrong.
Okay. So let's see what we had last class.
I realized mine.
We started with conditional probability. We said probability of an event A given another event is conditional probability. And conditional probability is very important part for probability and stochastic processes or signal processing. It's very important. We said we can break that down to probability of A and B over probability of B. So this definition for conditional probability makes another rule for us that was chain rule. That kind of finding probability of multiple events at the same time when happening, how we can break that down, A and B, or later A and B and C and D, whatever, it works for all of them. This is what we learned last class. We said, OK, if you make it more, A and B and C, still this works. Even for more, you just need to consider this part like another event like D, and then right here D, and then break that D based off the same rules. That's called chain rule. Chain rule is very important because these dependencies between events need to kind of break down. We also talked about another important part was total theorem. We said if we have, for example, 2 events like B1 and B2, and another event happening here like A, we can find probability of A is actually based off summation of probability of A given B1, P of B1, plus P of A given B2, P of B2. This was total theorem. That is very important. I think in your quiz, you should use this one somewhere. So we had this stuff last class. They are very important. But we made everything ready for something for today that called Bayes rule. That is very important. Like so far, whatever we mentioned, it was just some tools, like for modeling, for mathematical way. We had some examples, like practical examples, but they are still not that advanced problem solving. But the topic that we're going to talk today is very practical. Is based off this knowledge that we had last class, and is very practical. And that's called Bayes rule. OK, let's see what is Bayes rule. A little bit history. Thomas Bayes, he was one of amazing English statistician. In computer science or computer engineering and maybe robotics, 3 mathematicians are very famous. Bayes is one of them. Bayes, Gauss, and Newton. These 3 are kind of invented the basic fundamental of AI today, or robotics. We're going to hear about them a lot. Not Newton that much. Newton is mostly for dynamic and motion and differentiation and integral. And that was the first one, like I think 16th century. Yes, Isaac Newton was 1643 to 1727. 16th century, and then Bayes, 17, and then Gauss, 18. So, but these 3 mathematicians or scientists makes the backbone for modern computer science, signal processing, and what we call it today AI. And Bayes was actually, I can say, the most important the one was Bayes. We can see how, why. Let me clean this up. So what Bayes created was actually is about conditional probability. He mentioned that sometimes you can, because conditional probability in summary is the best prediction ever you can have. Best prediction, and our job, one of our job in computer engineering, electrical engineering, is prediction. We are trying to predict something based off whatever we have. Whatever we had before, we want to predict something that is supposed to happen, future. We want to actually predict that. And the prediction is based off Bayesian statistics. So Bayesian statistics telling us actually we can update a probability, like a probability of A given B, based off evidence. So the evidence is, let's call this X and Z, because X is better notation. So X is unknown, and Z is evidence. So this is the best prediction. We want to find something that we don't know, X. We want to find that given some information that we know about it, evidence. And Thomas Bayes kind of break that down, because this is very complex to compute, because this, we know about it, but we don't know anything about that. So Bayes mentioned that, OK, you have some evidence. You can update X. And also, he invented a method to evolve X, like find next X and then second X. And if there is like a process, like a robot that's moving, every time has one X, and measurements coming from the sensors, and we update the next and next and next, something like that. That also can be modeled with it. And so many other complex problems. That's why I consider Bayes as one of the scientists that without that, probably AI wasn't here now in this level. For machine learning, they're all is based off that. Yeah, application, lots of application. We're going to talk about this, lots of detail. Today we're going to go every part of this theorem and say how we can use it. But some samples, artificial intelligence based off, we call that Bayesian methods. Any methods after this idea, using this idea called Bayesian methods. So AI is mostly based off that, because in AI, we are predicting. We have some belief, and we update that. Every time measurements coming, we update that. Like, for example, large language models are doing the same way as well. They're kind of predicting as well, based off the information that you enter and the knowledge that it has before data, lots of data, they predict like next step. Or in robotic, you always predict next step based off the dynamic model, based off the previous knowledge. You want to predict what is the future, what is the next. And this is all a basic of AI is Bayesian methods. Most of methods, AI is so huge, so many different categories, but AI is one of them. Bayesian methods are one of them. Machine learning is the same. Machine learning is when you want to predict something based off the data. We are learn from data. Sometimes we call them actually data-driven methods, because they are based off the data. Based off the data that coming, lots of data, you are making a model, and this model is actually explaining when the input coming, what's going to be the output. So machine learning is based off that, like neural network, for example, or deep neural network, or convolutional neural network, working based off that. So neural network is like that. Training, let the neural network to get weight, because neural network is like linear equation. It's not complex, but has some weights. This linear equation has some weights. This weights coming from learning. Based off the data, we learn and we get those parameters, those weights. And after training, whatever input coming, the output going to get ready. That's a machine learning in a very high level. And decision making under uncertainty. So most of decision making that we have right now are not certain. They have uncertainty. We have some tolerance, we have some variance, we have some covariance. So Bayesian methods is one of the methods that can handle this uncertainty, can model this uncertainty. We can see that. And modeling, of course, probabilistic modeling is as basic of, as it's called, Bayesian modeling. You have a new method of thinking about things called Bayesian methods. Even thinking about things can be Bayesian. You can see how amazing is this theorem and how new ideas going to give you guys. For any other problem, I still trying to find new applications that we can use these kind of things. And you can use this application, use this theorem for other applications if you come to your mind. We can see that after learning that. I'm sure you're gonna have lots of ideas. And data-driven decision making that's coming based off the data that's coming is all based off Bayes' theorem. Because Bayes' theorem talking about updating a belief, we are believing that we're supposed to be here or this, and the data coming and we update it, and we go one step forward. We have a new state now. Again, we are in a new state. New state is our belief. And new data coming, we update it and go one step forward. And this is how this system works. So even you can model evolution using Bayesian models. Because it's evolving. Is it a process? If you bring time involved, it's become process. OK, so let's see how this works. So general explanation for Bayes' theorem is actually this sentence. How a belief can get updated when new evidence coming. So the new belief is the previous belief or last belief multiplied by new measurements. So let's write that in a mathematical way. So the new belief is probability. When we are talking about belief, means probability. Probability of something unknown given something known. Is this new measurements, P of z given x, we are around x, and predicted belief is P of x. We also have some normalization factor because that's going to be probability, so we need to add up to 1. So we always need to normalize it. So we have some normalization factor that is not a function of x. But what is important here for us, x? Z is given. You know z. So how we find x? Change that to optimization problem. We just need to say, OK, x is argmax of P of x given z. It means we find x kind of maximizing this. And that x is called prediction. If we put a hat on top, it means it has some uncertainty. This is called Bayesian inference. We're going to see that later. I just want to give you some idea what we're going to encounter with Bayesian. So this is called Bayesian inference because we took something out, this x. We infer that we like asking questions. When you model something, when mathematically modeling something, when you ask question about your model, that's called inference. You're asking question about the model for something that you don't know. And this is how we compute that. If you have a good function for this, if you have like break that down, because this can be complex, very complex, because it's dependency. And if you can break that down to multiplication or summation, that should be awesome, because multiplication and summation can linearly get solved. And when we make things linear, with linear algebra, you can, with very high speed, solve them. So that's the ultimate goal, to make everything linear, to can solve them fast. Okay? So that's the idea behind Bayes' theorem. Okay? Okay, I'm just going to clean this up and go further. So what this led us to do, we can reverse conditional probability using Bayes' theorem. Probability of, if you remember, here I wrote P of x given z is equal to P of z given x, P of x divided by P of z, that is just normalization, because it even doesn't have x on it in this part. There is no x. When you want to maximize or minimize, when you get differentiation or whatever method using, that's going to get out, because there is no x on it. That's why we most of the time take that out. We don't care about P of z. But if you want to compute it, you need to use total theorem for computing z. We can have some examples to see how we can do that. Anyway, this theorem tells us how likely hypothesis A is after observing evidence B. Here I put A is x and B is z. So you already have z. Z coming from sensors, for example, for the robot localization. There is a robot wants to localize itself. It has some sensors, some, for example, sensors that give you distance to surrounding. We call them IR sensors, infrared sensors. They send a signal and receive it and find the distance and wants to localize itself, where is in this environment. Okay? So these measurements coming, they are noisy, but still they are good. We have them every step. But what we want to find is something that we don't know, where we are, x. So we can find some hypotheses about x, that P of x given z, after observing these measurements, after reading these measurements. Okay? We're going to see how. Okay, in other words, learning from data. That's a very good explanation. Learning from data. You're going to learn from data. Learning means updating your belief. You're thinking this, but you're not 100% sure how we can update it, read some measurements, and update it. When you get new information, you update your belief. So updating the belief is Bayes' theorem. Updating a belief. Okay? So, because we're going to talk too much details now, I'm just going to need to go faster. The formula that we have for Bayes' theorem, we're going to prove it, is like that. We are saying probability of A given B is probability of B given A multiplied by probability of A over probability of B. So A is something unknown. P is something noun. And as you can see, this is reverse of that. And they have name. This is called posterior density. This is called likelihood. This is called prior information. And this is normalization factor. Normalization factor, prior, I'm going to explain them what they are. And posterior density. Because it's a density, it's a function. Okay, let's see each one by one. What is posterior density or posterior? So that's the result, what we want to find, updated probability. Updated probability is P of A given B. Or in our example, because notation for measurements is Z, notation for unknown is X, so that's why most of the time when I write Bayesian methods or similar to that, we mention P of X given Z. When I tell that, you're going to go, oh, X is unknown, and Z is something known. So that's just notations. You can, here we put A and B instead of them. Okay? That is posterior. Posterior is something that we want to find. The quality we care about. The second one is the likelihood. Anytime we have measurements involved, we have likelihood. Likelihood telling you how likely these measurements are given unknown. For example, let's tell you a very practical example. Imagine, robotic is the best example. Imagine there is a robot moving with this velocity, okay, and it has the position of x. It's two-dimensional, for example. So the state of this robot is x and v, for example. The state is a minimum variables that you can summarize something. So that's called the state. This state, we want to predict the next state. We want to predict the next state. So the next state is actually x, this is xk, for example. K is a time, for example. You want to find k plus 1 and vk plus 1. Even we want to find vk plus 1. So we have some, based off the dynamic that we had before, like a velocity that we had before, and where we were before, we can kind of predict where we're going to go after k step. Because this motion model, Newton invented that. Based off the motion model, you can find if you have time and if you have velocity, you can see how much you move after k second, for example, k step. So you can kind of roughly, you can say where we are. This is called P of A or prior. So the prior that I'm talking is some initial information about your belief. The belief is to find this. We want to find this. We have some a belief that we say, okay, we're going to be around here, but some information coming from sensors as well. Those information going to make this belief more precise. For those information, we have likelihood. So the likelihood is if you have multiple sensors, you have multiple likelihood. They just multiply together. It's OK. And prior is that knowledge that I explained. This is the prior that coming from the dynamic, for example, for the robot. And the rest is just normalization factor. Normalization factor is coming from total theorem. But in optimization, you just cancel that out because it doesn't have x on it. You want to maximize that function. When there is no x on it, it's going to get out. OK, that was one point of one view of Bayes' theorem with the function. As you can see, probability of A given B become probability of B given A. We are inverting. We are reversing conditional probability. We are reversing conditional probability. Another point that we can see that I already explained, we kind of mixing evolution using these Bayesian methods. This evolution coming from this. Posterior is P of x given z. I just use x and z to remind you which one is noun, which one is non-noun. Is a proportion. This sign means proportion. It's not precise. It's not equal. It's proportion of these two. Proportion is very important because it's showing how evolving. So it's a proportion of likelihood P of z given x, P of x. And in proportion, we remove that normalization factor. So in this case, we don't care about a P of z anymore. So for example, if you want to find x, x is equal to arg max of P of z given x, P of x. And these two all noun. Why? How P of x is noun? Any idea why P of x is also noun? What was P of x? Prior. Prior means something we know. Prior, in the example of robotic, was what we believe robots are supposed to be after 1 second. Because you had the velocity before, after 1 second, you can compute the next position. Just simple dynamic. You need just multiply velocity by time to find x. OK, so this is coming from this operation that I mentioned. And that proportion is coming from that. OK, so this highlight that a prior at time k is propagated posterior from time k minus 1. So it means k plus 1 going to be propagated posterior from time k, k plus 2 going to be propagated posterior from time k plus 1, and go ahead, future, and past 2. Kind of you can model world, everything, future, and you're modeling process of evolution, evolving. This was just evolving that x, for example, the position of the robot, but can be evolving whatever whatever x you think. Even this x doesn't need to be just one variable. It can be a matrix. It can be a function. Many dimensions. Many dimensions. It has many meanings. Many dimensions. It can be a view. Like, for example, this view is x. This picture is a view. It can be 3D. And you can evolve this by time, past and future. If you have enough information, those information coming from Z measurements, you can predict it. OK, so let's clear this up. So that's why this Bayes formula, Bayes modeling, Bayesian thinking is so important for us. For anything we're going to encounter in our future career or project, you can use these ideas. So in other words, the posterior is shared jointly by what we believe before and what data says. Data says this, and I was believing that. We combine them together to update that belief. Sometimes measurements not accurate as well. Sometimes our prediction was better than measurements. So they just cancel out those uncertainty. They fix it up. Maybe you heard about Kalman filter. Kalman filter is based off Kalman filter, another application of Bayesian models. We're going to see Kalman filter in the class. When we go for conditional probabilities in a better way, we're going to talk about Kalman filter as well. And we might have a project regarding to that. OK. So, and normalization constant is just rescales the result. It's not changing that. How prove it? So proving conditional probability is very, very simple. The idea coming from this, P of A and B is equal to P of B and A. So if you write PA given B, and if you write PB given A, because those two are equal, this and this are equal, you can put them equal. So the result's going to be what? PA given B, P of B is equal to PB given A, P of A. Done. It's proved. So it means P of A given B is equal to P of B given A, P of A over P of B. That's Bayes' theorem. Done. So even mathematically, you can prove it that is right. This is correct. Very simple. So it's not just assumption. It's something that directly prove based off axioms, probability axioms. We have a better version of that here. Any questions so far? I just try to explain Bayesian methods in a different ways and see the application. I just want to open your mind regarding to that, see how we can use that later. So another way can think about Bayesian is Bayesian thinking that I mentioned. Bayesian thinking means actually updating belief. That normally, actually in like a short term, I just can say Bayesian thinking means updating belief. You believe something, you update it. And go ahead, step by step. And is everything uncertain? Why everything is uncertain? Because measurements that you are reading from sensors are uncertain. When you buy a sensor, for example, it always has some tolerance. It mentioned, OK, it works in this dimension, for example, give you a distance like that with this variance, for example. So if tell you, for example, the distance to the wall is 2.5 meters, it's 2.5 meters plus some epsilons or minus epsilons. In that tolerance, that means uncertainty. And uncertainty can be modeled with Bayes, that we're going to see that. So belief after observing data is belief before observing data multiplied by data. And that data is a likelihood of data, of course, consistency with data. And as I mentioned at the beginning, it has lots of application, is robotic, obstacle detection, Kalman filtering. And we're going to see that. SLAM. SLAM is simultaneous localization and mapping. Simultaneous localization and mapping is a very like a hard problem that can be solved using sensor fusion. Can be solved like that too. Just for SLAM, I'm going to mention what is SLAM means. SLAM, you have, for example, agent or a robot and some obstacles. This robot's supposed to not just go to somewhere, also need to explore the environment. You're not just finding the trajectory, but also you find the position of obstacles. This is called the SLAM, very big, hard problem, but can be solved using Bayesian methods. This is called the SLAM, simultaneous, because at the same time, not just we localize. Localization means finding just position of the robot, for example. But mapping means finding the position of actually obstacle around us. OK? And sensor fusion as well. Sensor fusion is also Bayesian. When, for example, you have multiple sensors, most of the time, combination of two sensors that complement each other. A camera and LiDAR are very fit together, camera and LiDAR. But fusion of these two is very complicated because they have different space. The camera has a two-dimensional space, lots of, because of the lens, the things that you are seeing in a picture is not real. But in the other hand, the information that's coming from LiDAR is very precise and 3D points of the environment. How we can fuse these two together? Because LiDAR not give you colors, not give you like visualization of the 3D environment, just give you points, a cloud of points, millions of points. How you match each point to the picture or make these two as a 3D view of environment. That's called fusion. Sometimes we call it data fusion, sometimes sensor fusion is another application of this course or this class. We might see them more in examples or topics. So they are all working based off that. Measurements model and predicted belief or prior. This is prior. This is likelihood. New belief coming from that. We don't care about the normalization part because that's going to get out of formula. Doesn't have X on it. Example. OK, we have one example. In this example, we have a mobile robot using. I use examples of robot because it's more, you can visualize it. It's easier to understand these topics using robot. But if you don't like, you just can send me emails. I don't like robots, please. Make another examples. Like, I don't know, if you like playing with cards, I can do that too. But I think that's more relevant to your work. Okay, anyway, there is an obstacle in front of the robot. Okay, the robot is like that and has some sonar. It has a LiDAR. And we have an obstacle here. For example, there is a table here is an obstacle. And we define O as an event that obstacle exists. Okay? This is a good idea. Sometimes maybe obstacles not exist in that environment. So probability of O showing the probability of being this table in an environment. D is that sensor can detect that obstacle. So we have these two events. We have some data coming from before. We tested many times, and we realized, OK, probability of having obstacles is 30%. Probability of detecting obstacle is 0.9. And probability of a false alarm is 10%. So we know this information. The company that built that LiDAR, they give that to us. Okay, this LiDAR is great. It's expensive, but it works very good. It can detect objects in this probability, and false alarm is just 0.1%, just 10%. It's nothing, so buy it. OK, and we bought that, and we wanted to test it to see how that works. We want to see what is the probability of obstacle. Detected. Okay. So we want to find this. Based off, let's clean up this. So we need to see what is, OK, P of obstacle given detected is actually probability of detected given obstacle, probability of obstacles, and probability of detection. Probability of obstacle given, probability of detected obstacle given. We just need to find probability of detection. Probability of detection coming from total theorem. Remember, probability of that is detection, obstacle, obstacle, probability of detection, not obstacle, probability of not obstacle. So they are all given. first of all, probability of obstacle is this probability of not obstacle is 1 minus this. Okay? If we put them all together, 0.9 multiply 0.3, 0.1, 0.7, it's going to be 34. And if we put that here, it's going to be 34, 0.9, 0.3 is almost 0.79. Yes?
Reading. Could you reread that like top equation you wrote, like P of D equals?
Oh, P of D is equal P of D given, oh, sorry, I can next time write it better. P of D plus P of D given not O, P of not O, or complement O.
Thank you.
Yes, yes, you're welcome. Sorry, I'm going to write it better next time. Because it was last minute, I said, okay, finish it. Okay. Any question about this? So that part is coming from total theorem, but the rest is given. So we have another 2 more examples that we're going to talk about them in next class. Any question about this? We're going to have one assignment. You have 1 week for that. I'm going to just submit it today, probably.
Oh, nothing.
Why were you?
What I should know.
Chill.
What's going on in class right now? Except this one.
Well, students that are enrolled in
I went back and I read it again. I was like,
Economic design. No.
shit, that
Only assignment.
that's the students enrolled.
yeah. Well, I was thinking that too, but then I was like, and so it says students enrolled in